All right, and welcome back. 9.10. This should be the last one. And if you've understood what we were doing with Taylor polynomials, and this is not going to be that big a difference. So remember the idea, we started with Taylor polynomials where we were approximating, and what it really came down to is finding the value of these coefficients, which honestly really just came down to finding the value of the function and its derivatives evaluated at whatever our center value was. That was the calculation we had to do. Now, we did polynomials, and now we're talking about what happens if we take that out to infinity and we make a series out of it. And in particular, we make a power series out of it because we're going to have a variable involved. Remember, with power series, we have convergence one of three ways. Either at a single value, which is the center, we have it for all values of x, or on some interval. Okay? So the Taylor series and the Maclaurin series are not any different. They will do one of those three things. They're going to converge somewhere. And in general, we're going to get it on an interval, but there are some very nice ones that will converge for all values of x. All right, so that's the three things in Taylor series. Number one, actually finding the series or the series expansion. The second thing is showing where it converges. And the third thing is, does the value of the function actually equal the sum of the series? Because it's possible for it to converge and not equal the sum. Okay? It can be a very close approximation in a lot of cases, but it may not be equality. So those are the three things we really worry about. But for right now, we're just going to talk about what? Be right back. Okay, sorry. One of my nephews has shaved his head. Anyway, where were we? We were talking about Taylor series. So what we're going to start talking about to begin with is we're going to find the Taylor series, and then we'll talk about where it converges, which is just the things we did with power series using the ratio test and testing the endpoints. And then later, we'll do an example where we actually talk about representation. All right, so here's the first thing. If f of x is a function and it has a power series representation or expansion at a certain value, it is given by this. Now, there are other ways to find a power series expansion. If you look in the book, 9.9, I believe, talks about a way involving the geometric series that you can find power series representations. It's pretty neat. But since it boils down to doing the Taylor series anyway, I don't push it really heavily. All right? And Taylor series is exactly what we'd expect it to be. We have the same definition of our coefficients. It's just instead of going to a certain value, we go from 0 to infinity. Instead of being a polynomial, it's a power series, which means we have to check endpoints and find out where it converges. All right? Because it may not have an actual value everywhere, but we know what we're doing. And if C is 0, we get the Maclaurin series. Okay? At C, centered at C, about C, all of those are the same. All right, so let's start by finding a Maclaurin series or a Taylor series. I believe the first one is Taylor series. So find the Taylor series, or Taylor series expansion, sometimes it's called, for f of x equals 1 over x at 1. All right, and find its interval of convergence. All right, so we'll do this in a couple of things. First thing to do is to find the Taylor series, and before I find it, I'm going to make sure that I'm doing the correct problem. And find the Taylor series for f of x equals 1 over x at c equals 1. Yeah, this is good. So remember, what did we do? We had to find the values of the function and its derivatives at 1. So we're going to start with f of x. which is 1 over x. And then f of 1 equals 1 over 1, which is 1. Now, what we're going to do is we're going to look for some sort of pattern to these values. Okay? With the Taylor polynomial, we knew you take this many derivatives and you're done. With the series, we don't know how many. But we're going to look for some sort of pattern that evolves so that we can say, okay, this is what's going to happen. All right, f prime of x is going to be negative 1 over x squared. Therefore, f prime of 1 is going to be negative 1 over 1 squared, which is negative 1. Okay. F double prime of x is going to end up being positive 2 over x to the third. All right, double prime of 1 is going to be 2 over 1 to the third, which is positive 2. Okay, I'm starting to see a little something. It's going to be negative 6 over x to the fourth. So the third derivative here is going to be negative 6 over 1 to the fourth, which is negative 6. And one more, and I think I'll have it. I think I have an idea what's going on here. F 4x equals, well, if I take the derivative here, that's going to be 24, positive 24 over x to the fifth. And yeah, this is exactly what I thought was going to happen. 1 is going to be 24 over 1 to the fifth, which is 24. All right, so let's look at these values over here. This pattern may not be familiar to you because you haven't done this as much, but I've done it a lot. First of all, we're alternating positive and negative. So let's go ahead and I want to make some notations here. This is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, all right? So let's look at the numbers. Let's not look at the alternating pattern yet. Let's look at the numbers. 1, 1, 2, 6, 24. And in particular, let's look what happened. We had 2, then we had 2 times 3, and this is 2 times 3 times 4. In every case, the value of the number is n factorial. So in general, I can say that f5 of 1 is going to be n factorial, okay? But since I have the alternating part, I need this to go to negative 1 to something, and it's going to be negative 1 to the n. Now, you can have negative 1 to the n, you can have negative 1 to the n minus 1 or n plus 1. You've got to come up with a way to formulate this that matches what you have. So at n equals 0, I'm going to have negative 1 to the 0, which is positive 1, 0 factorial, and we said 0 factorial was 1. If n equals 1, we have negative 1 to the first, which is negative 1 factorial, which is 1, negative 1. N equals 2. I have negative 1 squared, which is positive 1, times 2 factorial, which is 2. If n equals 3, I have negative 1 to the third, which is negative 1 times 3 factorial, which is 3 times 2, 6, negative 6. In general, not 5, I'm sorry. This should be the nth. In general, the nth value of this is going to be negative 1 to the n over n factorial. All right, that's what we want to find. We want to find some sort of generalized way of writing that. So now, let's go back to what the Taylor series looks like. Taylor series is the sum from n equals 0 to infinity of f n of c, okay, and in this case, fn of 1, well, we'll just put c over here, over n factorial, x minus c to the n. So in our case, it's going to be the sum from 0 to infinity of -1 to the n factorial over n factorial x minus c to the n. And what's going to happen? Those n factorials are going to divide out. So really, the Taylor series is from 0 to infinity, -1 to the n, x minus c to the n. And that is the Taylor series for f of x equals 1 over x. All right. And sometimes you'll see this written, they'll clean it up a little more, and they'll say that this is n equals 0 to infinity of, I'm sorry, this shouldn't be c, this should be 1. Yeah, 1 minus x to the n. Because we can multiply -1 inside there and clean it up. All right? That's it. That is finding the Taylor series, and I would accept either one of those. So that's the first part. First part is actually is just basically finding the Taylor series. And the way you do that is you take the derivatives, you evaluate at your value of c, and you find a pattern. And then you have to find some sort of algebraic way of expressing that pattern. Okay? If you have something alternating, you're going to have -1 to a power. You have to make sure that your powers work out to make positive and negative like you want it. You know, the fact is this even or odd is going to matter. Okay? Look for patterns like, you know, the factorial. All right, now we're not through with this problem yet because we were told to also find its interval of convergence. Now, I'm going to do that. Remember, we do that using the ratio test. All right. And we want the limit as n heads to infinity of the absolute value, -1 to the n plus 1, x minus 1 to the n plus 1, all of that over -1 to the n over x minus 1 to the n, and that's going to be the limit as n heads to infinity. A lot of stuff's going to go away, and it's just going to be absolute value of x minus 1. Remember, when you take the absolute value of these -1 to the whatever's, they just basically go away. To the n plus 1 over n, that just leaves us one of these. As n heads to infinity, this limit is just going to be absolute value of x minus 1. All right, because n has absolutely no effect on this. All right, we have convergence when absolute value of x minus 1 is less than 1. Well, that is when -1 is less than x minus 1 is less than 1, which is when 0 is less than x is less than 2. All right. We have convergence from 0 to 2. We don't know what's going to happen at 0 and 2. We have to check those endpoints. So we would then plug 0, all right, into this. And I'm just going to look at this really quickly. -1, 0 is going to be -1. That's going to be 1 to the n. It's not going to converge at 0. It's not going to converge at 1. It's not going to converge at either one of those. All right. Now, I'm going to notate that. I'm not going to work it out. You can do it yourself, but we've done that work before. Will not converge at either endpoint. So the interval of convergence is going to be 0 to 2. If you plug in 0 here, you're going to get the sum of 1, which is 1 plus 1 plus 1 plus 1 plus 1. We've done that before. It doesn't converge. If you put in 2 here, you're going to get the sum of -1 to the n, and that doesn't converge either. You know, we've done that a couple of times in the 9.8. All right, so we did that. And the ratio test is not new. I did that just to show you that this is the same thing we did with other power series. Finding the Taylor series is not a huge deal. So I want to do one more series. In fact, I want to do a Maclaurin series. And then I'm going to show you something else. So the Maclaurin series I want to do is f of x equals e to the 4x. Maclaurin f of x equals e to the 4x. All right. So this is Maclaurin series. And we're not going to, all we're going to do here is find the expansion. That's all that we're asked to do. We're not asked to find the interval of convergence. So I'm just going to skip straight ahead to finding derivatives and looking for a pattern. All right, f of x equals e to the 4x. Therefore, f of 0 equals e to the 4 times 0, which is just going to be 1, because that's e to the 0. So what's the derivative of this? Well, f prime of x is 4e to the 4x. All right? And so then f prime of 0 is going to be 4e to the 4 times 0, and that's going to be 4. All right, you might be seeing where this is going. What's f double prime? Well, when you take the derivative of 4e to the 4x, you get 16e to the 4x. All right, this is f double prime of 0 equals 16e to the 4 times 0 equals 16. Is there a pattern? Yes. In general, the nth derivative raised to, the nth derivative of 0 is going to be 4 to the n. All right, that's just mathematically the way this thing's going to work out. All right, this is n equals 0, 4 to the 0 is 1. This is n equals 1, 4 to the first. If we did another derivative, what's going to happen? We're going to multiply by 4 again. It's going to be 4 to the third. Yeah. So in general, this is n, which means my Taylor series is going to be given by the sum from n equals 0 to infinity of 4 to the n over n factorial x to the n. All right. Why is it just x? Because it's a Maclaurin series. That's the reason this is 0. And so this is x minus 0, or just x. All right, so the work is not that hard. Finding patterns, finding an algebraic way to represent those patterns, sometimes a little difficult, but we can do it. One of the things I do want to say about Taylor series, I'm going to erase part of this. That if you know the Taylor series, you can actually do a substitution. Now, I'm going to find my notes here. I'm going to tell you that the Taylor series, that for f of x equals, where is it? E to the x, all right, you would get the sum from n equals 0 to infinity, x to the n, right, over n factorial. So if we had known this to start with, notice these are very similar. I could have just done a substitution. All right, then f of x, e to the 4x, would give us the sum from n equals 0 to infinity of 4x to the n over n factorial, right? If e to the x is x to the n over n factorial, e to the 4x, I'm just substituting 4x for x, just 4x to the n, and then you can just rewrite this a little bit. That's 4 to the n, x to the n, which you can see is exactly the same thing we have there. So if you know a Taylor series that's very similar to what you want to know, you can substitute in and find the new Taylor series. That's very helpful. In fact, there are standard tables of Taylor series. All right. So now what I want to do, remember there are 3 things we can do. You can find the Taylor or Maclaurin series. You can then show the interval of convergence. And the last thing, remember, is representation. And representation is really important because that's where you get the fact that the Taylor series equals the function. So here's the idea. We're going to define, again, Rn of x. This is the difference in the actual function value and the value of the Taylor polynomial at n. All right, this is the error when we approximate f with that. Here's what we want. We want R sub n of x to go to 0 as n heads to infinity. And if that's true, if the error goes to 0 as n goes to infinity, then we can say that the power series represents the function. And what does represents mean? That means f of x is equal to the sum, and I'm just going to write Taylor series here. All right? That's what represents means. All right, now you may notice that this is probably going to be some kind of bullcrap. I just really shouldn't say it like that. It's not going to be a direct thing. And in fact, we're probably going to end up using something we used before, which was Taylor's inequality. So I'm going to write Taylor's inequality right up here. It says that the Rn of x is less than or equal to x minus c to the n plus 1 over n plus 1 factorial, and then the maximum value of f n plus 1 of z. All right? So what does this mean? I really should not have written it there. Tell you what, let me set up the board and I'll come back.